nor the OH ion. In this simple preparation of a base, we'll add sodium, a very active metal, to water. First, we'll add a few drops of phenolphthalein to the water. There's no color change. Next, we carefully add a small bit of sodium metal. In this reaction, the sodium and water combine to form sodium hydroxide, a base, while hydrogen is given off. The phenolphthalein turns pink as the sodium hydroxide forms. This is the usual indication of a base. Bases are useful to us in many ways. For example, the solution commonly called ammonium hydroxide, a base, is the household ammonia we use. It emulsifies the greasy matter in which dirt adheres to our household things. Among the properties of acids and bases, we mentioned earlier that they react to form salts and water. In this case, where we are using a dilute acid and base, no visible reaction occurs. If we add phenolphthalein, it does not indicate a base. Evidently, the base was changed by the acid, or we can also say that the acid changed the base. If each kind of compound loses its characteristic qualities in their interaction, they can be said to have neutralized each other. We can use the term neutralization to indicate another property that results from the interaction of any acid with a base. When an acid reacts with a base, hydronium ions of the acid combine with the hydroxyl ions of the base. The resulting products are an ionized salt and water. Neither the original acid nor the base exists in the solution any longer. They have neutralized each other. Another way to express this is to say that an acid and a base react together to form a salt and water. So there is a direct relationship between acids and bases and the third kind of compound we are studying, salts. A simple definition is, a salt is a compound other than water that results from the action of an acid and a base in aqueous solution. Since acids and bases are usually such active compounds, we rarely find them free in nature. We do, however, find enormous quantities of salts in nature. The sea contains great quantities of various salts. These chalk cliffs contain carbonates, sulfates, and other salt compounds. What are some of the important properties of salts? One property is that many salts, such as sodium chloride, are very soluble in water. They dissolve readily. Like acids and bases, many dissolved salts are electrolytes, excellent conductors of electricity. When we test a salt solution, its conductivity is obvious. In water, the ions of the salt separate, and the freed ions in solution conduct electricity. Another important property of salts is their effect on the boiling and freezing points of water. Here we have boiling water, a boiling sugar solution, and a boiling salt solution. The sugar and salt solutions are of equal molecular concentrations. The beaker of water boils at 100 degrees centigrade, which is normal in this location. In this beaker, the sugar has raised the boiling point of water to more than 100 degrees centigrade. However, in this salt solution, a salt, calcium chloride, has raised the boiling point of water even higher than the sugar solution. The chemist calls this an abnormally high boiling point rise. A salt added to water also lowers the freezing point abnormally. In this comparison, we can see that the water in this beaker is freezing at 0 degrees centigrade, normal freezing point. Sugar in this water has appreciably lowered the freezing point below 0 degrees. But salt in this water lowers the freezing point abnormally, that is, below the sugar solution. How do we prepare a salt? We've already seen that one way to prepare a salt is by the neutralization of an acid and a base. But we can also prepare salts directly from their components, their metal and non-metal groups. For example, we'll make a mixture of this finely divided copper metal and powdered sulfur. Now we heat the mixture. The reddish copper and the bright yellow sulfur react to form a new substance, a salt. This black substance is the salt, copper sulfide. A salt can also be prepared from another and different salt. Earlier, you remember we made hydrochloric acid by reacting sulfuric acid with sodium chloride. Again, we have sodium chloride in concentrated sulfuric acid. Our products are hydrogen chloride gas and sodium hydrogen sulfate, a salt, different from the sodium chloride we began with. Sodium chloride is used in the preparation of many salts, acids, and bases. Sodium chloride is also our table salt, a useful flavoring for food and vitally necessary to our diets. Our household sugar is processed by the use of an acid, hydrochloric acid, as is the gelatin in desserts and other foods. Lye is an impure form of a base, sodium hydroxide. It reacts with the grease in a sink to form soap, which can be washed through the drain. The mortar in which bricks are set is made in part from another base, calcium hydroxide, or slaked lime. Spreading a salt on ice lowers the freezing point, helps to melt the ice. We constantly use the properties of acids, bases, and salts in many ways. When we take milk of magnesia to counteract stomach acidity, we are using a base, magnesium hydroxide. An acid, hydrofluoric acid, is used to etch glass. The glass bottles and other glass equipment you use in your chemistry lab may have been treated by hydrofluoric acid to etch the numerals into the glass. Among the many acids we use, sulfuric acid is one of the most important. The storage battery in your car contains a solution of about 40% of sulfuric acid. The uses of sulfuric acid, both in industry and in the lab, are numerous. It has been said that the amount of sulfuric acid a nation produces is one index of its prosperity. But perhaps we can expand this statement and say that a nation's industrial position is related to the volume of its production of acids, bases, and salts.